Hello everyone, today we'll talk about the problem nth Tribonacci number. This is a sequence defined in a way analogous to the Fibonacci number sequence, which starts 1, 1, and every next number is the sum of the two previous numbers. 1 plus 2 is 3, 2 plus 3 is 5, and so on. And in this case, as the name, the part try suggests, we start with 0, 1, 1 as we're given, and so the next number is 2, because it's the sum of all those. The next number is 4, is the sum of all those. Then we have 1 plus 2 plus 4, which is 7, 2 plus 4 plus 7, which is 13, and so on. I'll show you a number of solutions to this problem, but the basic idea of the simplest solution, which is why this problem is considered easy, is to just do as the definition says. Since the definition is recursive, when we want the nth one, then we have to add up the n minus first, n minus second, n minus third, and so on. However, of course, the obvious caveat here is that whenever we calculate a previous number, we don't want to calculate it more than once. Because in this case, now for n minus 1, we have to take n minus 2, n minus 3, n minus 4, and this is the same, and this is the same. And since every step along this pyramid, the number of recursive calls grows by a factor of 3, right? So here are 3, here is 3 times 3, here we would have 3 cubed. That becomes unmanageable very quickly. These numbers grow exponentially because the way to calculate them also has an exponential number of steps. However, between position 0 and position n, there are only n plus 1 different numbers. So if for each of them we calculate something in essentially constant time, then we can calculate the nth number in linear time, and this is what we want to do. So we want to essentially take our simple recursive method that just follows this definition given in the task statement and make it not calculate any value more than necessary, more than once. Here is how you can do it in Python. In Python, you can utilize this cache decorator from functools, and in that way you can just implement your function to calculate those Tribonacci numbers in a usual way. So if n is 0, we return 0. If n is 1 or 2, we return 1. Otherwise, we recurse, so we call this Tribonacci on numbers from n minus 3 to n, not including n, so n minus 3, n minus 2, n minus 1. We sum them, and this is our result. So this thing here is the slow solution, and this simple decorator makes it fast. And in case you're interested in how this decorator works, or perhaps you want to implement it yourself, or you don't know that this decorator exists, one way you can think about it is that you have the outer function which just keeps a dictionary for memoization, and whenever the value n is already in the dictionary, it just returns it. Otherwise, it calculates it. Here we recurse on that outer function. So it just calculates the value at that position, remembers it in the dictionary, and returns it. And in that way, whenever we ask again, for instance, for the Tribonacci number of 7, then we just have it in our dictionary, we can return it, instead of calculating and doing recursion and other things like that. So this is enough to solve this problem. However, I'd like to talk about some few other things and approaches. One thing to notice is that we can of course use this decorator. That's the simplest and probably fastest way in terms of time spent writing the code. However, you can also of course calculate those things iteratively, since you can just start with essentially 0, 1, 1 as a list, and then you add to it the sum of those, so 2, you add to it 4 for as long as necessary, and then you return the number n. And in case the problem was more like you get t test cases and every test case asks you for the nth Fibonacci number, not Tribonacci number in this case, then it would be nice, because when you calculate it, it will truly be only calculated once. So if at some point you're being asked to give the 30th and then you're being asked to give the 12th, then you already would have at position 12 the correct value. Since we're here only asked to provide the nth number once, we can take this solution and optimize space for that solution. In that case, we can only keep those two numbers, three numbers in this case of Tribonacci numbers. So we start with 0, 1, 1, and for as long as one of those numbers is not our solution, which is defined by n being greater than 1, we'll decrease n by 1 and move this window in this imaginary array one step to the right. So if we have 0, 1, 1, then this one comes here, this one comes here, and this thing becomes the sum of all this. And again, this one comes here, this one comes here, so this is 1, 2, and this is 4, which is the sum of all those, right? So this is a simple space optimization, so we only keep three numbers. In Python you can write it like this, so you take the last two numbers, you unpack them so that they become single integers, and the last one is the sum of those values. And of course then you return the nth one from this smaller three-element vector. And now here is a bonus with which perhaps some of you are unfamiliar. Notice that these operations are quite simple, and in fact every element of the resulting vector is constructed as a sum with some weights of the elements of the previous vector. Because this one is a sum with values 0, 1, 0, this one is with values 0, 0, 1, and this one is with values 1, 1, 1, right? Because this is 0 times this, plus 1 times this, plus 0 times this, so it's simply this value. Same for this one, 0 times this, 0 times this, plus 1 times this, so only this value, and this is of course the sum. Takes this, this, and this. And what operation do we know can calculate for every position here the value as a sum, as a weighted sum of values previously? Where that operation is simply matrix multiplication. So we can either implement matrix multiplication ourselves, or we can use a library that does it for us, for instance NumPy. And in that case we just define our vector, which is still 0, 1, 1, and we define our transformation in terms of a matrix. So this is the matrix I talked about before. And now for as long as necessary we transition, and that transition is simply matrix multiplication of vals by this matrix. And the idea here, of course, again, you can think about this multiplication as placing the vector here, here placing this big matrix, which is two-dimensional. And so let's rewrite it. And value at position here in the resulting vector is the sum of this times this, plus this times this, plus this times this. So here 0 times 1 plus 1 times 1, 0 times 0, so this is 1. Here 1 times 1 is 1, rest is zeros, so it's 1. And here of course values are all ones, so 0, 1, 1, that's 2. And then if we multiply it by that matrix again, we get the next step, right? And of course the idea with matrix multiplication here is that if we take vals and then we multiply it by m, and then we multiply it by m, and then we multiply it by m, we can, since the way matrix multiplication works, we can, instead of, for instance, calculating it like this, we can place those parentheses in another way. In particular, we can calculate vals times m to the third. And of course, if you've ever thought about how to quickly exponentiate numbers, you can do the same with matrices. So we can use binary exponentiation, which is of course the fact that when you take m to some power, then it is approximately equal to m to that power over 2, and that whole thing squared. And perhaps you have to, right, multiply it by m again, in case that p was odd and not even. And you can implement it yourself, or again, since we're using NumPy, we can just utilize the fact that NumPy implements it for us. So we can use just the matrix power. So essentially we raise m to the power of n minus 2. Perhaps we get identity matrix in that case if we raise it to the power of 0. We adjust n so that it is in range 0, 1, 2. and we return the result. And the advantage of this solution, as you can notice, that the matrix power will raise m to the power of e in about log e times, of course, something like m to the third or something like that, but we don't care about that since that is small. Something like log e time complexity. Then we can answer, in case we were being asked, for instance, to provide numbers modulo some big prime, then we can be answering not only queries about the 30th Tribonacci number, but about Tribonacci number of index that has 20 digits, and it would still be doable. So this is quite an advanced technique, and I think it's pretty beautiful that you can use something that's completely unrelated in general to what we're typically doing. But yeah, simply we can think about this as matrix multiplication. In that case, we can quickly exponentiate the matrix, and that gives us the ability to calculate the number at a given index very quickly. And this thing is of course applicable to normal Fibonacci numbers as well. And the rule, since matrix multiplication is just linear combination of elements of the input vector, so it's the weighted sum of those. So if our recurrence is also a weighted sum that doesn't depend on the number of step, for instance, and does not multiply things with each other, then we can easily do it like this for any such recurrence that is only a weighted sum, or a simple sum in this case where we have only ones and zeros. So this is more of a, for readers who are interested, or watchers who are interested in more advanced techniques.